Hi everyone. In this session, we are going to discuss about work. The word work in our day-to-day life we use very commonly, right? No, when we write, when we read, when we eat, when we walk, all these things we used to consider it as doing work. But when we come to physics, the word work has a special meaning. Okay. Simply, if I push a ball, I'm spending energy, but still I cannot tell that I have done some work. So there are some conditions in physics that we have to tell that we are done some work. The first condition is that when we apply force, there should be a change in position for the object. Okay. So when we are applying some force on an object, the object should move. That is the first condition. Okay. Or else we can tell that work is said to be done if there is a change in position of the object due to this force. It should happen with this force. Okay. Same way, if I stretch this rubber band, it changes position or changes its shape. Right? No? Same way, I have a ball with me. When I press it changes shape. So in both these conditions also, I applied force. Right? Okay. So this is the second condition, or we can consider the second point as by applying the force, if it makes any size or shape change is there, we can consider that also as work done. Okay. Or we done the work. So we can commonly define work as work is said to be done if the force applied on an object moves it or make any size change or shape change. Then at what condition we can tell that there is no work is done? If we apply a force but if there is no movement or there is no shape change or phase change, we can tell that there is no work is done. Like I am pushing the ball. Actually I am applying force here. But according to physics, I did not do any work. Same way, if we have a very heavy load with us. Okay, very heavy weight. You have to lift it up. You are not able to lift it up. But you have to spend the energy. There also we feel that we have done some work. But the output is not there. But in physics, we never consider it as work done. Or, okay, you're going somewhere and your car got stuck somewhere. It's not restarting. So, obviously, what we used to do, we used to get out from the car and we used to pull it. So, consider that your father is there, he is trying to restart the vehicle and you are coming behind the vehicle and you are trying to push it. But think that you are not able to make a small movement. Okay. So there also we are applying all our energy, but still there is no movement for the vehicle. That time also in physics, we used to consider it as the person didn't do any work. So if the work has to be done, two conditions should be there should be a movement. Okay. Or there should be a size or shape change. If these conditions are there, we can tell that the person did some work. We will state it which are the conditions or the factors which affect the work done. Conditions, we can tell that there should be an application of force. Okay, there should be an application of force and that force must change the position or size or shape of the body. That is the condition. Now, if we state in terms of factors, first one, magnitude of the force applied. There should be a force and it should have some magnitude. Magnitude of force and there should be a movement, or in terms of factors we can state that the distance moved by the object in the same direction of the force applied. Distance move due to the force in the same direction of the force applied, the same direction of force. Okay, so these are the two factors which affect the work done. First one, magnitude of the force, and second, distance moved by the force in the same direction of the force applied. If we increase the magnitude of the force, the work done will increase. Okay, same way, if the distance moved by the object increases, it increases the work done. Okay, now we'll see the definition of work done. The work is defined as the force applied on a body is equal to the product of the force applied and the distance moved by the body in the same direction of the force. Or we can write it in terms of equation. Work done is used to represent by the letter W, or work is equal to force into distance. Okay, work is equal to force into distance, or as in form of equation we can write it as F is equal to F into D. Force into distance or displacement. If force is 0, that means if we did not apply any force, the work done is 0, that condition is not going to happen. The other condition, if the displacement is 0, force into 0 is equal to 0, work done is equal to 0. So that is a common way how we will get work done as 0. There are some special conditions. Not only this displacement is 0, there are some special conditions. If the displacement is there also, in that particular examples, we will get the work done as 0. Let us see how it is. Actually, when you come to 10th standard, we are studying the equation as F into D cos theta. Okay, this cosine is a factor that you will study in mathematics. It's a trigonometric factor. Okay, so there are some particular value for this one. Theta means it's the angle. Okay. So if cos 0, if the angle is 0 degree, cos 0 is equal to 1, and if the angle cos 90 is equal to 0. It is a particular value assigned for cos 0 and cos 90 degree. Okay. Now, if the object is, consider that you have an object here and you applied force from here. Okay. And what happened? The object moved towards this direction and now this is the present position. Okay. And it moved a distance D. So work done is equal to F into D. What is the angle between F and D? Force and displacement is in the same direction. Means the angle between F and D is 0. Okay. So cos 0 is equal to 1. So we will get W is equal to F into D into 1. That is equal to F into D. So this is the condition what we used to study. We used to see the coolies or the porters. They used to carry weight on their head. Okay. Just consider that this is a weight upon a coolie. Okay. It's a person who carries a weight. Okay. So, if the person simply standing like this way, the person is doing some work. Or when he carries a load, simply if he stand means there is no movement, his work done is 0. But actually the person is carrying the weight, right? Spending energy. For our concern, in common concern, he is doing some work, but in terms of physics, he doesn't do the work. But when he lift it up, he is doing work done against the force of attraction, or he is lifting the object. That time he has done the work. Now consider that he started moving. So the weight of the object is always acting downward direction. So F is acting downward direction and the person is moving towards this direction. So here D is towards that direction. Okay. So when we see the angle between force and displacement, it comes 90 degree. So when we apply in this case force is there, that's a weight acting downward direction, and displacement is there, how much the coolie moved, into cos 90 degree. Cos 90 degree is 0. So finally we used to tell that if a coolie carries the object upon his head and moving, in effect according to physics, he doesn't do any work. Same way the orbital motion, or you just tie some chalk piece or stone and just round it. In that case also we used to consider it as there is no work done. The same case we can consider for the rotation of earth around the sun, or the movement of moon around the earth. So there also the angle comes at 90 degree. So just consider this is a path or the movement of earth or moon. Just consider here we have the earth. Okay. We know that there is always an attractive force towards the earth. Okay, just consider here we have the moon, and the attractive force is always acting like this way. This is our F. Okay. When we consider the direction of this moon, at this position, this is the direction. Okay. At this position, this is the direction. So the force is acting here. Just consider this angle. It makes 90 degree. Just consider this angle. It also makes 90 degree. So actually, if the earth is revolving around the sun, or moon is revolving around the earth, we used to consider it as it is not doing any work due to this 90 degree. So these are some exceptional cases. So wherever we get the angle between the force and the displacement or the distance is 90 degree, the final work done will be 0. Otherwise, so that's why we used to tell that there should be a force or magnitude of force should be there, and there should be a displacement of the body in the same direction of the force. Now we'll see the unit. So we studied that work is equal to force into displacement. What is the SI unit of force? It is Newton. What is the SI unit of distance? It is meter. So work is equal to Newton meter, or we used to consider it as joule. Joule, because this work is equivalent to energy. The common unit, the energy, the unit of energy, we used to consider it as joule. That's why instead of this Newton meter, only for work we can write it as joule. Last session we studied about the moment of force. There also we are using Newton meter, but we cannot write it as joule. Moment of force, the unit should be Newton meter. But work done, if we get the unit as Newton meter, we can write it as joule. The reason is that the work done is equivalent to energy spent by the object or the person. So we'll define 1 joule. So 1 joule is equal to 1 Newton into 1 meter. So 1 joule work is said to be done if a force of 1 Newton acting on a body makes a movement of 1 meter in the same direction of force applied. The higher units of joule is there. 1 kilojoule, that is equal to 1000 joule. Again bigger one is a 1 megajoule. Mega means it's 10 to the power 6. Okay, 10 to the power 6 joule. And instead of Newton, it can be weight. So how we are representing the weight? It is kilogram force. So 1 kilogram force is equal to 9.8 Newton, or we can consider it as 10 Newton. Okay. So 1 kilogram force is equal to 9.8 Newton, or we can round it off it as 10 Newton. Thank you.